So let us recall our previous discussion. We introduced AC electric circuits during the last lecture. In particular, we discussed what happens if we attach an active resistor to some AC power supply and inductor to AC power supply. So what is the phase shift between current and voltage when we have active resistor in AC electric circuit?
No difference.
No phase shift, so phase shift is equal to 0. That means that current and voltage are changing over time in the same phase if we have active resistor. What happens if we have inductor?
It is shifted by pi over 2.
So in which direction? So with respect to voltage, current is lagging behind by phase shift pi over 2. And we also introduced the concept of inductive reactance, which is equal to omega times L, the inductance. So this parameter is equivalent to resistance in DC electric circuit, so it's opposition of inductor for charge transfer in AC electric circuit. This inductive reactance is proportional to the frequency, so it increases as frequency increases because it's a product of frequency like omega and inductance. What is the reason for this dependence? Why active resistance doesn't depend on frequency, but when we have an inductor, inductive reactance is frequency dependent. We discuss this.
Increase in frequency cause the faster change of the flux.
So the higher frequency, the higher rate of change electric current. So if we consider the first derivative as the measure of changing rate of electric current, and recall this Faraday's law, which tells us that we will induce electromotive force proportional to the rate, means it will be higher for higher frequencies. Then we understand that this induced electromotive force will oppose any changes in current within the AC electric circuit, and will be negative polarity with respect to driving power supply, AC power supply. So that will cause some opposition to electric current, to AC electric current to flow through this circuit. That's why inductive reactance increases as frequency increases. So that's only one component of AC circuit. So we consider active resistor, but that's a classical example. So then inductor, but we also have a capacitor, and that should be discussed today. So let us consider an AC electric circuit with inductor, with a capacitor. So let's assume that the AC power supply provides voltage, the instantaneous voltage as delta V maximum times sinus omega t. And here will be some voltage drop delta VC over this capacitor with capacitance C. So again, according to the second Kirchhoff's law, we can write that delta V, like voltage applied to the circuit from the AC power supply, minus Q over C will be equal to 0. So Q over C, that is potential difference between the plates of the capacitor. So now we can substitute here the expression for time dependence of this delta V. So it will be delta V maximum times sinus omega t minus Q over C, that is equal to 0. And next step, we solve it with respect to Q, to electric charge accumulated at the plates of the capacitor. So that will be equal to C times delta V maximum times sinus omega t. So this we have, and now we have time depends, so we can show it like Q as a function of time. So we have this time dependence of electric charge accumulated on these plates of the capacitor. How do we go from this function to time dependent current through this circuit? We take first derivative over time according to the definition of current, which tells us it's electric charge transported per unit time through the circuit. So that's why we can write that electric current through the instantaneous electric current through the through the capacitor will be equal to first derivative of Q over time, and that will be equal to omega times C times delta V maximum times cosinus omega t. So at this point, we can apply a trigonometric identity, and cosinus omega t we can represent as sinus omega t plus pi over 2. So now instantaneous current through the capacitor will be given as omega times C times delta V maximum times sinus omega t plus pi over 2. So now we see that like voltage is changing proportional to sinus omega t, and current is changing proportional to sinus omega t plus pi over 2. So there is a phase shift between current and voltage, but in this case, current as opposite to inductor will lead the voltage by phase shift 90 degrees. So if we take a look at this slide now, let me share this slide with you. That's how we see this time dependence of current and voltage. We see the phase shift between them, but in order to show it better in terms of phase shift, we should look at the phasor. And here we see phasors are moving counterclockwise. So current phasor is ahead of voltage phasor, and there is 90 degrees phase shift between them. So we had opposite situation for inductor. As you remember last time, it was pointed here. Current was lagging behind. So now we can also write the expression for maximum current. I maximum will be equal, according to our equation here. So this is this part. So it will be omega times C times delta V maximum. And this can be written in a bit different form. Delta V maximum divided by 1 over omega C. So again, we can rewrite it by introducing, similar to inductive reactance, we can now introduce capacitive reactance. So it will be delta V maximum over XC, where XC is capacitive reactance, and that is 1 over omega C. So we see that, similar to inductive reactance, capacitive reactance is also frequency dependent. However, it behaves differently. So if we consider frequency approaching to 0, what will be with capacitive reactance? Will approach infinity. So what does it mean? That capacitive reactance for a DC current, because if frequency approaches to 0, that we're approaching DC current, will be equal to infinity, which means that DC current basically is not capable of flowing through the circuit with a capacitor. And that makes sense because capacitor is just the insulator in between two plates. So we have open circuit. By definition, in such circuit, we cannot cause like steady state DC current. We discussed that DC current may flow once we only turn on the circuit and we have some transient processes which happening very quickly while we charge capacity. But if we're talking about some steady state condition, obviously current cannot flow through such a system. So we see here that besides this fact that DC current cannot flow, inductive reactance decreases as frequency increases, because it, as opposite to inductive reactance, it stays in the denominator. So what are your suggestions how we can explain it from physical point of view? What do you think, guys? So we know already the reason behind linear frequency dependence of inductive reactance, because of the rate change of electric current, higher rate, higher opposition to charge transfer because of Faraday's law. But here we have different reason. Any suggestions? Let's assume that that's actually the case. Capacitance is frequency independent. It doesn't change with frequency. So only parameter is ohm. Now assume that you have some capacitor with fixed capacitance, given number, and frequency of AC current, let's say 10 hertz. So 10 times per second, actually it will be 20 times per second because we will charge it positively, discharge, and then charge it negatively. Just will change polarity, but we will pump twice charges through the capacitor per one period of AC current. So that means that with a frequency of 10 hertz, we will charge and discharge this capacitor with given capacitance 20 times. The voltage, the maximum voltage, dV maximum, is fixed. So we don't change this voltage of the AC power supply. So voltage is fixed, means maximum voltage up to which we can charge the capacitor. And what it means? That there is maximum electric charge which can be pumped into the capacitor. So, and this maximum electric charge will be defined by what? If we know voltage, the potential difference between electrodes of the capacitor, and capacitance. The product of capacitance and voltage, they give us the charge, the magnitude of electric charge, which can be accumulated. So now, keeping this in mind, that we can put some limited amount of charge every time we charge to maximum our capacitor under given conditions, we remember now that for 10 hertz we can charge and discharge 20 times. So there is some fixed, like maximum electric charge, which can be transported through this capacitor per unit time, because it will define how many times per second, means 20 times per second, we can charge and discharge. It's 20, so we have maximum voltage, the delta V maximum times capacitance times 20, because that's how we charge and discharge 20 times. So we pump it in and change polarity, again charge and discharge. So that will be our total charge which was transported through this capacitor. Capacitance times potential difference times 20, because frequency is 10. Now, what happens if we increase frequency? Let's say we go to 100 hertz. We keep the voltage the same. Voltage doesn't, the maximum voltage doesn't change. Capacitance is the same. We only change frequency. So instead of charging and discharging this capacitor 20 times per second, we will do this 200 times per second. So it means we will like push through this capacitor one order of magnitude already higher electric charge per the same unit of time, per the same per second. Means electric current will be 10 times higher. The magnitude of AC electric current will be 10 times higher, because current is defined as first derivative of charge over time. So delta Q over delta T. Delta T is the same, but delta Q is 10 times larger. In this case, current is 10 times larger. Means that at frequency, higher frequency, we deal with lower capacitive reactance, because there is less opposition of this capacitor to electric charge transfer in the AC circuit. So that's why we observe this frequency dependence of capacitive reactance, and as we increase the frequency, we increase number of charges, discharges per unit time, and that allows us to run larger current. Means if the voltage remains constant, this guy should decrease as frequency increases. So that is the reason why we observe capacitive reactance uh, decreasing as frequency increases. So we have opposite dependencies on frequency for inductive and capacitive reactances. So now let us consider so-called RLC electric circuit when we have all components together and connected in series. So we have power supply, AC power supply, instantaneous voltage delta V maximum sinus omega t. Then we have delta VR. This is our active resistor, inductor, and capacitor. Delta VL. And here we have delta VC. So these components of the AC circuit are connected in series. So what does it mean? That the current will be the same and in the same phase for all components of the electric circuit because they are connected in series. So we can write that, let's say this is our supplied like voltage at the terminal of the AC power supply, but current in this circuit, let's say we can show it like this. That doesn't make much sense, but just I as in the AC circuit will be represented as I maximum times sinus omega t minus phi, where phi is the phase shift between established current in this RLC electric circuit, AC circuit, and applied voltage to this circuit. So our goal obviously to understand what will be this current, the magnitude, maximum amplitude value of the current, and what will be the phase shift. While current is the same, but we know that for different components of AC electric circuit, there will be different phase shift between current and voltage drop over each of these components. So we can write now that delta VR will be equal to I maximum times R times sinus omega t. And that will be the VR sinus omega t. So voltage drop over active resistor, then we have dVR, not dVR, dVL. That will be I maximum times XL, which is inductive reactance, times sinus omega t plus pi over 2 that will be delta VL times cosinus omega t, and delta VC will be I maximum XC times sinus omega t minus pi over 2. That is equal to minus delta VC cosinus omega t. So here we show the voltage drops over each of components of these circuits, AC circuit, and with respect to voltage which is applied to the circuit from the AC power supply. So the total voltage can be represented here. So what do we see here in this left side? That these are phasors for current, voltage drop over active resistor, inductor, and capacitor. So these phasors are rotating counterclockwise with the frequency omega. But what is important here, that we have in opposite phases voltage drops over inductor and capacitor, because you remember we had phase shift minus pi over 2 for inductor and phase shift plus pi over 2 for capacitor, means the phase difference between them is 180 degrees, which is pi, means they are changing in opposite phases. So they always, in each given moment of time, they kind of compete with each other and counterbalance each other. So depending who is larger, so in this case, voltage drop over inductor is larger, so the difference will be positive in this system of coordinates. So it will be difference between voltage drops over inductor and capacitor. Then we have this component along axis y, we have component along axis x, which is change like voltage drop over active resistor, and the total like voltage drop will be defined as like vector sum of these two phasors, a resultant phasor from originated from reactive components of the AC circuit, and phasor originated from the active component of the circuit. So resultant will be theta V max, and there will be some phase shift between current and resultant voltage in this electric AC electric circuit. And this is the angle, like phase shift phi, which we want to determine. But first, we get the expression for the impedance of AC electric circuit. So from the previous figure, which we considered on the slide, we can write that delta V maximum, the magnitude of this phasor for maximum potential difference, will be equal to square root of delta VR in second power plus delta VL minus delta VC in second power. So what we can do here, we can represent this potential differences under the square root as products of maximum current, which is the same for all components, and their either active resistance or reactive resistors, depending which components we are considering. For delta VR, we can write I maximum times active resistance R in second power plus I maximum times XL for delta VL minus I maximum XC, and this difference in second power. So this will be equal. What we can do here, we can factor out I maximum because it's the same for all cases. I maximum square root, and what we have left here, it will be R square plus XL minus XC square. Or in other words, it will be I maximum times Z. We can call it like this, amplitude of the, like magnitude of the impedance of the circuit. So we can write that I maximum will be equal to delta V maximum. So that is the amplitude of the voltage which is provided by AC power supply divided by Z absolute value, like the magnitude of impedance of this AC circuit. And in other words, we can express it as delta V maximum divided by square root of R square plus XL minus XC square. So that is the expression for the magnitude of electric current. It's like our first question. We wanted to figure out what will be the magnitude of, if we know maximum voltage applied to this AC circuit, we need to divide it by the magnitude of impedance. So why I'm talking about magnitude of impedance? Impedance is a total resistance or position of AC circuit for charge transport, and it takes into account all features, active and reactive components. Since it has two components, so active originates from active resistor, obviously, and reactive originates from inductive and capacitive contributions. So since it has two components, it's actually a complex quantity, complex number, and impedance Z is expressed as Z prime plus I times Z double prime, where Z prime is the real component of this imaginary quantity impedance, and Z double prime is imaginary component. So in our case, we have the following situation. It can be written as R instead of Z prime. The real component is actually our active resistance plus I times XL minus XC. So I is square root of minus unity. And from mathematical point of view, the product of plus I gives us phase shift pi over 2, and minus I is phase shift minus pi over 2, which corresponds to the inductive and reactive components of the electric circuit. So how we can represent it? We can actually show it in graphical form, the impedance. So here we have Z double prime, imaginary part of impedance. Here is Z prime, real part of impedance. This is the magnitude of impedance, Z, like length of this vector in real imaginary system of coordinate. And this is angle phi, which is phase shift. So here, if we consider projection, it will be R, active component of the impedance, and here XL minus XC on imaginary axis. So now we can express this angle phi. So angle phi can be determined as arc tangent. From previous figure, let's show it again. Here, it will be this can be determined by the potential differences over active and reactive components of AC circuit. So we can write arctangent of delta VL minus delta VC over delta VR, or it can be expressed via the imaginary and real components of the impedance from this plot. So it will be given as arctangent of XL minus XC over R. So now we can determine both magnitude of maximum current which flows through the AC circuit, RLC circuit, where we divide maximum voltage provided to this circuit by AC power supply divided by the magnitude of the impedance of this AC electric circuit, determined with this equation. Next step, we can also determine the phase shift between current and voltage established in this electric circuit, and it can be done either by dividing the resultant potential difference, like voltage drop over reactive component of the electric AC circuit, divided by potential drop over active component of AC circuit. Or we can operate with the ratio between imaginary component of impedance and active component of, like, real component of impedance. So with this, we provide whole information about conditions of current, like charge transfer in RLC circuit, and we can determine magnitude and phase shift of electric current with respect to applied AC voltage. So we will continue next time with AC circuits. We will introduce electric power, which is dissipated over such RLC electric circuit. And also we will spend some time discussing transformers and rectifiers, how we can change the voltage in AC circuits, and also how we can convert AC current into DC current. So these are topics for next discussion. Thank you very much for your attention and have a good evening.